filters. This example is going to concern an RF bandpass filter, BPF. Now, if you recall in the last lecture, I told you that any prototype low-pass filter can be transformed to any other kind of response. It could be a bandpass filter, it could be a high-pass filter, or a bandstop filter. Okay, so if you compare this circuit, and this is where we started. Okay, how it can be transformed to a bandpass filter? If you just look at the elements, well, what all you have to do is to replace this C with a parallel LC element, like this. Okay, and let's call this L1. This is C1, and for the series inductors, you have to replace the series inductor by a series LC combination. Okay, then let's say we are going to have C2 with L2. Similarly, we're going to have another inductor in parallel with C3. So this could be L3, and then we are going to have a series C3 over here. Okay, we have C3, so this is C1, C2, C1L1, C2L2. Let's have this as C2. Let's have this as C3. Never mind. So let's have this as L4, C4, and in there again we are going to have a shunt inductance before the load, and this is going to be, if this is C5, this is going to be L5. Okay. So what we have done is we have replaced the shunt reactive elements, whether they are capacitor or inductor, doesn't matter. But the shunt, in this circuit, shunt capacitors have been replaced by a shunt LC element, parallel LC branch, and the series inductors have been replaced by the series LC branches. Okay, the idea is simple. I mean, what happens is that your series LC branch is now going to resonate at the center frequency of the bandpass filter. That is, it will be equivalent to a short circuit. It will be equivalent to a short circuit at the frequency, at the resonance frequency omega naught, which is determined purely by the reactive elements. Okay, let's see, this is LC, so omega naught equal to at one frequency, at omega naught equal to square root of LC, you're going to have a perfect short. That is, the transmission is going to be seamless, right? It's going to be, it's a short circuit, so you're going to have a maximum power transfer, right? Then the other idea of replacing your shunt branches with a parallel LC branch is that, again, at the same resonant frequency, your parallel LC element is going to behave as an open circuit. Okay, so this is going to be an open circuit at the same frequency. So this is open circuit at the same resonant frequency, omega naught equal to 1 square root LC. So what happens at omega naught 1 over root LC is that this shunt branch is going to be open, and this is going to be short, open, short, and open. So at omega naught, if this is my frequency scale omega, this is the frequency variable. So at omega naught, I'm going to have maximum transmission. Okay, so this vertical line is where I'm going to have maximum transmission, and then on either ends, this response is going to fall off at either end. Why? And it's going to fall off symmetrically. Why? Because the impedances are going to pick up. Okay, the shunt susceptances are going to pick up, the series impedances are going to increase, and then you are going to have impedance on either side of omega naught. And also recall that the 3 dB frequency, this is the band for the low pass filter. This is the point. If this is 0 decibels transmission, if this is the perfect transmission from source to load, then the point at which your response is going to fall off by 3 decibels is the 3 dB frequency. So let's call this as omega 1. And this is omega 2. So the difference of omega 1 and omega 2 is your 3 dB bandwidth of a bandpass response. So the bandwidth, let me write this down, is this is equal to omega 2 minus omega 1 minus omega 1. Okay, that's your bandwidth. Okay, And the quality factor, let's define the quality factor as well. This is another important parameter associated with the bandpass response. It's the center frequency divided by the bandwidth, and it determines how selective is your bandpass response. For example, if the bandwidth is very narrow, then it's going to allow very selected range of frequencies strictly, not allowing any stray frequencies to pass through. So for very narrow band low pass filter, we are going to have a high Q band pass response. Okay. So this is another factor which measures the sharpness of the response, let's say. So the idea is to just to replace your LC circuit element, your series inductor with the series LC element, and your shunt capacitor in this case is going to be replaced by the parallel LC branch, which is going to act as an open circuit at the center frequency of the bandpass filter. Okay. Now, one more thing is that your inductor and capacitor, they're going to contribute equal reactance. That is, for that, well, if you're going to, if you write this as omega L for the series branch, omega L minus 1 over omega C, and well, this is your series branch reactance. And if you're going to differentiate this with respect to omega, okay, if you do that, so let's do that. This is another important thing. This just tells you the rate at which the reactance change with respect to the frequency. This is L minus, well, omega comes up, so this becomes plus 1 over omega square C, right? Omega square C. So you should be able to see that the derivative of the reactance with respect to omega at around let's say omega naught, which is the resonance frequency. The rate at which the reactance falls off with respect to the frequency around omega naught, 1 over square root LC, is at the rate of twice L, right? If you're going to substitute omega naught for here, this is 1 over square root LC, C goes out, and then you're left with twice L. So the rate at which the reactance falls is about twice L. And if you show this for the parallel LC branch as well, you'll find out the rate at which the reactance falls is twice the rate of capacitance. Okay. So due to this reason, you have to, whatever is the value of the inductor, you have to divide that by 2. You have to divide that by 2 because the inductor and capacitances are going to contribute equally, and at resonance, the inductor or capacitor is going to have reactance which is going to fall off with respect to the frequency on either side of omega naught at twice the rate of that inductor or capacitor. Okay, so you have to divide that by 2. So what I mean is that in designing of a bandpass filter, you have to keep a few things in mind. First, you have to replace the parallel branches, the shunt branches, with parallel LC combinations. Series branches are going to be series LC sections, okay, and this is going to continue, okay. So let's understand this with an example first of all. So we again have to use the results of problem 4.1 in the last lecture to design the 5-element bandpass filter with a Chebyshev 0.5 dB ripple shape, and let the input and output impedances remain at 100 ohms. Okay, so the scaling factor is the same. The center frequency is to be 5 megahertz. The total bandwidth between outside 0.5 dB band is to be 200 kilohertz. Now, if you recall, the low pass filter that we constructed last time was having frequency about 100 kilohertz. This frequency is the passband edge, okay, and this is the bandwidth of the low pass filter. Now, what we are going to do is we are going to transform this DC to another high frequency at 500 kilohertz. We are just going to shift this DC to 500 kilohertz. This is going to be the center frequency of the bandpass filter, and on either edge, we are going to have a response like this, and on either edge, this is the maximum transmission at 500 kilohertz. On either edge, we're going to have the bandwidth. This will be, okay, how much it was? It was 5 megahertz. Sorry, it's 5 megahertz. Okay, so this is 5,000 kilohertz then that means this is going to be 4.90 megahertz, and then another 3 dB point is going to come at 5.1 megahertz. Okay, that means the bandwidth is about 200 kilohertz. Just like the bandwidth of a low pass filter, this is the bandwidth of a low pass filter. Okay, so we are going to have this bandwidth on either this 3 dB point is going to occur on either side of the band pass filter, and we are going to have a bandwidth of 200 kilohertz. Okay, so let's see. This was my low pass filter. Okay, this is my low pass filter, and now what I've done is to replace this capacitor by a parallel LC combination. And how it is done is that first of all, this 27.15 has been reduced by half because LC are now going to contribute equally, and with twice the both reactances are going to contribute equally, and the rate at which at center frequency they are going to fall off is twice the capacitance, twice the capacitive reactance. So they have to divide by 2. Okay, once you divide this by 2, this capacitance, this is 13.6 nanofarads. Then what you do is to find the corresponding inductance which resonates at the center frequency of the bandpass filter. You just have to plug in the value. Okay, so you have just use 1 over square root LC, which is equal to 2 pi into 5 megahertz. Okay, 5 megahertz, that is 5 into 10 to the power 6. Okay, you just have to substitute those values and you find out the other corresponding reactive element. So the capacitance is 13.6 nanofarads. If you do the calculation, you will find out the inductance comes out to be 74.5, and this combination resonates at, this combination is going to resonate at 5 megahertz, and you have to do this for all the rest of the elements. For example, the series inductor is 195.7, and half of this value is 97.85. Okay, and then corresponding C has to be calculated using same resonance formulation, right? And this repetition is repetitive. So on either side, the inductor is 195.7, so this becomes half, and then you find out the same capacitor corresponding to that particular inductor, which is going to resonate with that inductor at 5 megahertz. Okay, and then you do the same calculations just like you did for the first shunt branch. For the shunt branch in the center, this is 40.44 nanofarads, just divided by half, and then find the inductor, okay, which corresponds to resonating with the corresponding capacitor at 5 megahertz. Okay, now if you simulate the circuit from 4 megahertz to 6 megahertz, this is what you get. This is a typical bandpass response, and you see at 5 megahertz we have the maximum transmission. This is minus 6.022 dBs, and this is Chebyshev response. So 0.5 at minus 0.5 dB, this is the last ripple which occurs at the edge of the passband, and this occurs at 4.9 megahertz. So this is as the filter has been advertised, this is how it behaves, right? So this frequency, I mean, this is the center frequency, this is the 5 megahertz frequency, and from here we can see that this is 4.9 megahertz, and the other passband edge where the last 0.5 dB occurs is at 4.9 megahertz, right? And this occurs at minus 6.5 decibels, right? So we have two edges which are being shown by M2 and M3 markers, and again you have the frequency, the bandwidth of this low pass filter is about 200 kilohertz. Okay, it's 200 kilohertz. If you're interested to know the quality factor, well, just take the ratio of the center frequency, that is 5 megahertz. Okay, I can write this as 5000 kilohertz divided by 200 kilohertz as the bandwidth, center frequency or the bandwidth. So this comes out to be equal to 25. Okay. So yes, it is a high Q bandpass filter, which means it's a very selective bandpass filter and going to provide high attenuation to the frequencies which are beyond the passband. So this is your transition band. On either side you have the transition band, and the filter is providing the attenuation to all those frequencies, right? You can see this on the vertical scale. These are the undesired frequencies. It's going to pass, it's very selective in nature, it's going to pass the frequencies in the 200 kilohertz passband range around 5 megahertz. It's going to reject the other frequencies. Okay, so it's a very good filter having a very high Q. Let's take the last example. This is about the high pass filters. What the problem says is that, well, your high pass filter are derived again from the low pass filter that you talked before. So how you do this, you have to change the inductors to capacitors and vice versa. And replacing the component values in the prototype low pass filter, you have to do this by reciprocal. So 2 farad, for example, capacitor is now going to be a 0.5 inductor. So the prototype high pass response at omega will be equal to the prototype low pass response at 1 over omega. So you have to convert the low pass filter into a high pass filter, and next you have to scale it to the cutoff frequency of 5 kilohertz to operate at 50 ohms. So that is 50 ohms, the both source and load impedance. Finally, convert this scale filter into a bandstop filter with the stop band at 10 kilohertz, centered around 500 kilohertz. Right. So this is a prototype low pass filter, and to convert this to a high pass filter response, all you have to do is you have to replace this capacitor by an inductor. Okay, then this inductor is going to be replaced by a capacitor, and the reciprocal is 0.5 farads. So the values are also reciprocated because you see J omega L is the reactance, inductive reactance. So the capacitive reactance is the reciprocal to that. So it's the reciprocal of the capacitances and inductances respectively. So this becomes an inductor as well. And if you visualize the response, well, at low frequencies, the inductor is going to be short-circuited. At DC, the capacitor is open circuit. So there is no transmission. Okay, if you do that, okay. So this is Henry's. This is Henry's. So the response is simply transformed from low pass to a high pass like this. Okay. At DC, there is not going to be any transmission. The transmission will start occurring. I mean, you can consider any, for example, 3 dB point. This can serve as a passband edge. Okay. So this F naught is any passband edge having certain tolerance. It could be, for example, -2 decibels, -1 decibels, whatever it is. Okay. But this typical configuration is that of a 3-section high-pass filter. So let's see how we can make the design to satisfy a 5 kilohertz cutoff frequency and a 50 ohms operation. That is, both are scaled by 50 ohms. That means the inductor is going to be scaled by 50. They have to multiply this by 50, and then you have to divide this by 2 pi into 5,000. Okay, why you do that? Because you have to denormalize the scale, right? You have to denormalize the scale. Okay. So I have first of all a normalized high pass filter. So you see the reciprocals of 1 farad is 1 henries. Okay. R means that we are considering an ideal low pass filter with an infinite component quality factor. The coils have no resistance. Okay. Although they have a finite resistivity and the respectable inductance or number of turns are going to produce certain ohmic resistance, but for simulation purposes we are considering 0 ohms. So okay, this 1 farad capacitor transforms to 1 henry inductor, shunt inductor on either side, and this inductor is going to be transformed into a capacitor. Okay, the capacitor is going to transform to an inductor, and the values are reciprocated. Okay, now if you do this simulation, this is for a low pass filter because this is generic, right? And the response is that of a Butterworth filter. This is not a Chebyshev. So you will see this is the magnitude response. It's not in dBs, and it's a normalized magnitude response because the maximum scale is 1. It has been normalized with the maximum output power. This is the power response. Okay, right. Now, where does the half power point occur? The half power point occurs 0.5 transmission, 50% transmission occur at around again 0.159 hertz. Okay, or 159 millihertz. Okay, it's the one and the same thing. So at 159 millihertz, we have 50% power transmission. This is the high pass response, but this is the normalized high pass. So this is a normalized NHPF, this is a normalized high pass response. Well, how to denormalize? It's simple. Just you have to multiply this with 50 if it's a 50 hertz operation. Okay, of the load and the source is 50 hertz. So that's the 50 hertz source, and then you have 50 hertz load. And well, if you don't have the same reactance, same load and source impedance, you might need to include LC matching sections for that, right? You have to do this with the impedance matching networks. Okay, we are not going to get into that. There are some video lectures, you can go and watch them for LC matching and for pi matching or T matching networks. We have different topologies for impedance matching networks. But if the impedances are different, you have to consider an impedance matching network in between, right? So to keep the thing simple, I mean, to keep the power matched at the center passband or from the passband edge, we are keeping the load and the source resistance is equal. Okay. All right. So if it's 50 ohm operation, then the inductances are going to multiply by 50, and the capacitance is going to be divided by 50. And then it's not only that, you have to divide this by 2 pi into 5000. Why? You have to denormalize the scale, right? You have to denormalize the frequency scale. So if you do that, and then you have to do this for all the lumped components. So this is the third order Butterworth high pass filter, and if you do the same over here as well, you have to divide this by the same factor. This is the circuit you're going to get. Okay, this is a third order Butterworth low pass filter, third order Butterworth low pass filter. Oh, sorry, the high pass filter, third order HPF, and this is denormalized. Okay, and this operation is happening at 50 ohms. So what happens here is, you see the half power, 50% power transmission is occurring at how much? The scale is in kilohertz, so this is 5. So we have denormalized the scale, right? By dividing the components by 2 pi into 5 kilohertz, you have denormalized the frequency scale, and by multiplying the components by 50, we have a circuit that transfers half the power at 5 kilohertz as required. Okay, and you can see that for higher frequencies, which above 10 kilohertz and so on, 12 kilohertz, you have the maximum power. The normalized maximum power transfer is for high frequencies is 1. Okay, this is again the normalized power response. Okay, this is the magnitude of the power. So it's Pn of f. This is the normalized frequency transfer, frequency axis. Okay, normalized with the maximum power. So the maximum is 1, is unit. Okay. All right. Now the last thing was to transform the question. The last thing was the transformation. You have to convert this scaled filter into a bandstop filter with a stop band of 10 kilohertz, and this stop band has to be wide. The stop band has to be wide at 10 kilohertz wide. This is the bandwidth of the stop band, and the center frequency or the notch frequency is 500 kilohertz. Okay, so that means what we're going to do is, just like for a band pass filter, you have to go do the reverse. Okay, so instead of a series inductor, you have to replace this with a parallel LC combination, and those series capacitors, shunt capacitors, originally have to be replaced by a parallel combination of LC elements. Why? Because the parallel LC LC branch is going to resonate at 1/100 LC frequency determined by the components. Frequency determined by the component, but this is going to be an open circuit. Okay, this combination is going to be open circuit at the center frequency, and this combination is going to be a short circuit at the center frequency. So what happens at the center frequency of 500 kilohertz? You are not going to have any transmission. Okay, and then the frequency, because we are transforming the low pass prototype to a band stop, and the transmission, the passband edge was 5 kilohertz. So on either side, we are going to have twice of 5 kilohertz, that is 10 kilohertz wide stop bandwidth. Okay, so that means well, you see what's going on is, again, you have to divide this inductance by 2, because inductor and capacitor are going to be going to contribute equal reactances. So this, you're going to have a capacitor over here, and then from 1/100 LC, you have to find out, you have to consider 2 pi if you're considering the frequency in hertz. So this is 500 kilos. Okay, 500k. So you have the inductor value, right? And if you just evaluate the expression, you will find out what C is, corresponding C is. Similarly, you have to do the same for the shunt LC branch. Now, this is we are going to have a band stop right now. So for band stop, this is going to be divided by 2. Okay, and then you have to find the corresponding inductance L. Okay, and so you have to do this same for again another shunt inductor. The values are going to be the same because you have done this before for this shunt branch. So 1.59 divided by 2 is about 0.795, and the corresponding capacitance that resonates at 500 kilohertz is 127.45 picofarads. And similarly, you see 0.3183 by 2 is about 0.1592 microfarads, and the corresponding inductance is 0.636 microhenries, which is going to resonate at 500 kilos. And then you have the same shunt branch on either side of the load, 50 ohms. And if you're going to simulate you're going to do the linear AC analysis from 470 to 530 kilohertz. That involves the center frequency of 500 kilohertz. You're going to get a bandwidth. This is again the normalized power response. Okay, why? Because it's consisting of V out squared. Okay, and the load was 50 ohms. So this is power, and then you have to denormalize with the maximum. If you don't denormalize this, then this 1 becomes 0.005, right? So this is a normalized frequency power scale. This is a normalized power scale, power frequency response. So the point at which 50% transmission is occurring, there are 2 points, and these points are denoted by the markers M1 and M2, and the values are specified over here. This is about, so the transmission where the 50% occurs is about 495 kilohertz, and then you have 505 kilohertz. The difference is again how much? It's 10 kilohertz. That is what was desired, right? So that is what was desired in the question. So we have the stop bandwidth of 10 kilohertz, and this is centered at 500 kilohertz. Why? Because we have set the lump components to resonate at 500 kilohertz. 500 kilohertz. This circuit is going to be open circuit. This is open circuit. So there is no transmission. You can see a frequency dip, right, like this. Okay, we are not going to have any transmission at 500 kilohertz. So that is how the filter is behaving. And then these elements, these shunt elements, these shunt branches are short circuited at the same time. So you don't have any transmission, right? At 500 kilohertz, this is the center frequency of the bandstop filter, and there's no transmission. But the idea is the same. You have to start with a normalized low-pass filter, okay? That's where we started off, and from normalized low-pass filter, you can either design a high-pass filter, or a band-pass filter, or a bandstop filter. All you have to do is to denormalize for a given scaled resistances. You have to scale your reactive elements, inductors and capacitors accordingly, and then you have to denormalize the frequency scale by dividing the reactive element values by 2 pi into whatever the frequency of the passband edge is, or the center frequency is. Okay, so this is transformed to a denormalized low pass filter or a high pass filter like this. Once you've done that, for band pass or band stop, you have to add another reactive element, either in shunt or in series, depending on if it's a band stop or a band pass filter, and the combination has to resonate at the center frequency. Okay, and this is going to create a band pass or a band stop response. So the normalized low pass filter can be transformed to any other kind of filter by following these steps. Okay, so that's all.